This video covers motion graphs and kinematics. One graph that you might see on a position versus time graph is an object that is stationary. What that means is that we're staying at the same position over time. So we shouldn't have any slope whatsoever. If we are staying at the same position over time, then we have zero velocity. If we have no change in velocity, then we also have zero acceleration. Another situation would be a constant non-zero velocity, basically just saying a velocity something other than zero. So one situation might be a constant positive velocity. What this means is I'm covering in the positive direction 2 meters, let's say, in 2 seconds. And if another 2 seconds pass, I should have gone another 2 meters. Okay, this is what it means to have a constant velocity. So here, if I see a positive slope, this is telling us a positive velocity. So our slope tells us velocity. So on a velocity time graph, I should show that my velocity is the same over time. If my velocity does not change, then I should have an acceleration equal to 0. This would be the same thing if we had a situation with a negative velocity. Again, a negative change in position over time. So let's say I go negative 2 meters in 2 seconds. A negative 2 meters later, I should have gone another 2 seconds. On a velocity time graph, this would have looked like a constant negative velocity. And that should be a straight line. A constant negative velocity. Again, if we have no change in velocity, then we have zero acceleration. Remember that the situation would have also been the same if I went from a negative position towards 0. So even though it looks like my velocity is negative because it's under the graph, that's not the case. I'm still going from a, let's say, negative 10 to a, let's say, negative 5 position, meaning that I'm moving in the positive direction. So I do have a positive velocity or positive slope here. So a velocity time graph would have shown a positive velocity. And again, no change in velocity means zero acceleration. Now the really important part is when you're slowing down or speeding up. There's two situations you need to remember. An object will only speed up if the velocity and the acceleration are in the same direction. So one of the most common mistakes is that if you see a positive velocity, people automatically assume that you are accelerating in the positive direction or that you're speeding up, and that's not always the case. So if you have a positive velocity and a positive acceleration, you will speed up. But you will also speed up if you have a negative velocity and a negative acceleration, which is the case when you are falling. You're falling downwards. The acceleration due to gravity is also downwards. So that's why you speed up when you fall down. An object also will only slow down if the velocity and the acceleration are in different directions. So again, just because you have a negative acceleration does not mean that you will automatically slow down. So a situation like a negative velocity and a positive acceleration, you are slowing down. Same thing if you had a positive velocity and a negative acceleration, you are also slowing down. So this situation is probably the hardest example that you'll see. You have an object that follows a path on this position time graph that I drew. So again, what we're going to do is draw tangent lines that'll help us kind of figure out what's happening with our velocity at different points. So at this point, I have a negative velocity, and I can tell by my negative slope. So I have a very large negative velocity. Sometime later, I'm still going to have a negative velocity, but now it's not as large as it used to be. And then again, sometime later, I'm going to have a velocity of 0. So what that means, if I go from a very large negative number to a 0, is that I'm slowing down. So starting from a negative number, let's say 10, I'm going to slow down until I hit 0. If you don't have any numbers on your graph, it's a good idea just to kind of make up some numbers that will help you figure out what's happening. So here I have a negative 10 meters per second velocity. Sometime later, I'm at negative 5 meters per second. So again, that tells me I've slowed down, and then sometime later, I've hit a velocity of 0. So I've stopped at this point. My acceleration comes from my slope. Gives me acceleration. So my slope here is a positive slope. So this is a positive acceleration. Now this makes sense because if I have a negative velocity and a positive acceleration, it means I'm slowing down, and that's consistent with what I see in my other graphs. So on an acceleration time graph, this would look like a positive constant acceleration. So we are looking at only constant situations here. Another situation that gives students a lot of trouble is this one on my position time graph. So again, I'm going to draw my tangent lines to help me figure out what my velocity is at different points. So here, I have a flat line, meaning 0 velocity. Sometime later, I have a slope, but it is a negative slope, so a negative velocity. And then sometime later, I have still a negative slope, but it's even steeper than it was before. So again, what's happening is I go from 0 to something small negative and then something large negative later. So to show that on a velocity time graph, I want to make sure that I'm going from 0 and increasing as time goes on. So a 0 velocity at this point, let's say a negative 5 meters per second sometime later, and then sometime later I'm at a negative 10 meters per second. So again, if I look at what's going on here, I have negative velocities. If I look at the slope of the velocity time graph, I have a negative acceleration. So a negative velocity paired with a negative acceleration tells us that I'm speeding up. So now this negative acceleration I want to show on an acceleration time graph. Because it's negative, it needs to be below our x-axis. So this would show a negative acceleration. There are also a lot of other situations with graphs, but we're going to see a little bit more of the examples in class. So now we're moving on to kinematic equations. These 3 kinematic equations are the only ones you truly need to memorize. This one down at the bottom is something that is not on your equations table, but it's also a good one to help you in case you don't have acceleration. Then you don't need to solve for it, and it makes some of your calculations a little bit easier. So just to go through, our notation is a little bit different from last year. Here we're using knots to represent initial. So these little O's down here are called knots, N-A-U-G-H-T. So this is velocity knot, and this is position knot. And both of those mean initial, so initial position, initial velocity. When they don't have anything at all, then it's final. So here we don't have anything, so it's final velocity. Here we don't have anything, so it's final position. Time is still the same, and acceleration is still the same. So just to tell you a little bit more about where these kinematic equations come from. Remember last video that we said area under a curve is displacement, or area under the curve of a velocity time graph is displacement. So down here we have a velocity times time. Again, what this is doing is finding the area of this particular rectangle. So velocity, which is your height, times change in time, which is your base, gives us this area. So this is the displacement in this particular amount of time. So that gives us that first part of our kinematic equation. The second part comes if we have been accelerating. So again, because it's a triangle, we have 1/2 base times height. Another way to write our height or velocity is acceleration times change in time. if you notice that this is our acceleration equation rearranged. So putting it all together, the displacement we have when we accelerated plus the displacement we had we not accelerated, adding those two things together would have given us our change in position, or displacement. To find our second kinematic equation, we look at a velocity time graph. Here, we can see that for our velocity time graph, that the slope gives us acceleration. If we rearrange this equation around, then we get our kinematic equation. Remember that for a graph, this is very similar to y equals mx plus b, where on the y-axis we're going to have final velocity. Our slope is going to be acceleration. On the x-axis we have our change in time, and then our y-intercept is our initial velocity. But we're used to seeing it as final velocity equals initial velocity plus acceleration times time. But it's the same thing. And our last official kinematic equation comes from substituting in v is equal to v naught plus at. Solving this in terms of t, so I get v minus v naught divided by a is equal to t. And I go back to the first kinematic equation, and everywhere I have a t, I substitute in this new piece. So with some algebra, it simplifies down to this piece. So for extra credit, I want you to bring this derivation completed into class next time I see you. And to get full credit, you need to show all of your work, meaning every single algebraic step that you took, I want to see. So the last thing, what makes last year's problems and this year's problems so different are the fact that we're going to have multi-stage problems. What that means is that the acceleration is not constant all the way through. Then we need to break this up into two pieces. So basically, if the acceleration changes, then it is a new and separate problem. So treat it like individual pieces. Also, something to help you is that the ending velocity for one part is the initial velocity for the part after it. So if I start from 0 and I speed up until I get 5 meters per second, this was the final velocity in the first problem. But then let's say I travel for constant speed after that. Then this is the initial velocity in the second part. So the ending velocity for the first part is the beginning velocity for the second part. Also, if you're asked to find total displacement, and again, you're not accelerating or the same all the way through, or you're not traveling at a constant speed all the way through, then you do need to treat them as separate pieces. Basically solving the displacement separately, then add them together. Taking into consideration the signs. So if it's positive, keep it positive. If it's negative, keep it negative. Also, if it's asking for the total time, the same exact situation, then solve for the time in each phase separately, then add them together. So just to give you an idea of the kind of problem that we're going to see in class. It says a car is at rest at a traffic signal. When the light turns green, the car accelerates at 2.4 meters per second squared for 15 seconds. Then the driver maintains a constant velocity for 0.8 kilometers. Finally, the car slows to a stop in a distance of 180 meters. So here, I color coordinated that you can see we have 3 different parts to this problem. In the first part, we're accelerating. The second part, we're moving at a constant velocity. And then the third part, we're also accelerating, but we are slowing down. So, because we're moving in the positive direction this entire time, our acceleration at the very end is negative, And we should know that because we are slowing down. We don't know what the number is, but we already can tell that that should be a negative number. Because we are moving at a constant velocity in the middle, then our acceleration was equal to 0, like we saw in our motion graph problem. And at the beginning, it does say that a car is at rest at a traffic signal. So again, giving you some of those subtle pieces of information. Again, just something that we're going to be seeing a little bit more in class of.